Lecture 9 is all about integrating combinations of trigonometric functions. Suppose, for example, I want to integrate sine to the mx times cosine to the nx, where the power of cosine is odd. This looks complicated, but in fact a simple substitution will work. So if I let u equal sine x, I can use one of the cosines in du, which is cosine x dx, and then the remaining powers of cosines I can break into a product of cosine squares, and cosine squared of x is 1 minus sine squared, which turns out to be 1 minus u squared. So everything converts to something in the new variable u. Here's an example. If I want to integrate sine to the 5x times cosine cubed x dx, I let u equal sine x, then du is cosine x dx, and cosine squared x is 1 minus u squared. Here I split away one cosine for du, and then the other cosine squared I convert to 1 minus sine squared. So my integral becomes the integral of u to the 5, sine to the 5, times cosine squared, which is 1 minus u squared, times cosine x dx, which is du. And this is relatively simple using the techniques from Calculus 1. I get the answer in terms of u, and then I convert back to functions of x. The same strategy works even if a sign doesn't appear in the function. So suppose I want to integrate cosine to an odd power, say cosine to the 5, I can still use the substitution u equals sine x. I split the powers of cosine, I split away one cosine for du, and then the even power of cosine I convert to a function in sine using the formula cosine squared equals 1 minus sine squared. Letting u equal sine x here, I get du is cosine of x, and then cosine to the 4 is cosine squared squared, which is 1 minus sine squared squared, which is 1 minus u squared. At the end of the day, I end up with an integral of powers of u, which again is relatively easy to compute, and then when I'm done I replace the u's by my function of x, which is sine of x. Suppose now I have an odd power of sine, then I can use the substitution, or I have the option of using the substitution u equals cosine of x, and du is then sine x dx, and the sine squares convert to 1 minus cosine squared, which is 1 minus u squared. And again, this same technique will work even if the power of cosine is 0, even if I'm just talking about the integral of sine to the mx. Let's look at the example sine to the 5x times cosine to the 4x dx. Here my previous strategy, letting u equal sine x, will not work because the power of cosine is not odd. However, I can let u equal cosine and convert the even powers of sine to powers of cosine. So if I let u equal cosine of x dx, I'm going to convert minus sine x dx to du, and I'm going to convert every sine squared to 1 minus cosine squared, which is 1 minus u squared. The integral of sine to the 5 times cosine to the 4 is the integral of sine to the 4 times sine of x dx times cosine to the 4x. And here I'm splitting away this single power of sine to use as du. Then I have the integral of sine squared squared times cosine to the 4 times minus du here. And this converts to the integral of 1 minus u squared squared times u to the 4 times minus du, and again I'm just integrating powers of u, which is relatively easy, and I then convert them back at the end of the calculation to functions of x. Again, the same substitution will work for any odd power of sine. I don't need to have cosines in the function. Suppose both powers are even, then neither of the above strategies will work. If both powers are odd, I have options. I can choose either of the strategies. But if both powers are even, then neither of those strategies will work. And I get around this by using the half-angle formulas from trigonometry. So we have sine squared is 1/2 times 1 minus cosine 2x, and cosine squared is 1/2 times 1 plus cosine 2x. For example, if I have the integral of sine squared x times cosine squared dx, I can convert both of these using the half-angle formula, and I end up with the integral, when I multiply what I get from sine squared with cosine squared, I end up with 1/4 times the integral of 1 minus cosine squared 2x dx. So that's multiplying the half-angle formula for sine squared by the half-angle formula for cosine squared. And now this is the integral of 1, which is easy, minus the integral of cosine squared 2x, and I have to apply the half-angle formula again to integrate cosine squared 2x. Now in this case, if you check it out here, cosine squared of x is 1/2 1 plus cosine 2x, so cosine squared 2x is 1/2 1 plus cosine 4x. Now we end up with the integral of sine squared cosine squared, the original integral, is 1/4 the integral of 1 minus cosine squared 2x, which is 1/4 the integral of 1 minus 1/2 times 1 plus cosine 4x dx. That's a relatively easy integral, and you can do that with Calc 1 techniques. Note that we could also switch the even powers of cosine or sine to powers of the opposite function, sine or cosine, and we could use the reduction formulas that we introduced in the last lecture. We'll have a look at those again. We saw in the last lecture that using integration by parts, you can prove that the integral of cosine to the n is given by this formula, which reduces the problem to integrating cosine to the n minus 2. And we have a similar formula for the integral of sine to the n. I could use this to integrate sine squared times cosine squared. By converting the sine squared to 1 minus cosine squared, then I'm integrating even powers of cosine, and I can use this formula to reduce all of these even powers by 2 until I get to either cosine to the 0 or cosine to the 1. Suppose I want to integrate secant to the power of m times tangent to the n dx. This is a rather scary looking integral. If m is even, that means I can split off a secant squared. And remember that the derivative of tangent is secant squared. So I could try the substitution u equals tangent of x. And we also have this formula relating secant squared to tangent squared. Secant squared is 1 plus tangent squared. So I could convert the remaining even powers of secant to powers of tangent. Let's look at an example. Here we have an integral of secant to the 4 times tangent. We certainly have an even power of secant. And I break that up into secant squared times tangent. I use one of these secant squareds as the derivative of my substitution u equals tangent of x, and the other one I can convert to powers of tangent. So letting u equals tangent of x, we have du equals secant squared of x dx, and then the other secant squared is 1 plus tangent squared, which is 1 plus u squared. So, at the end of the day, I have the integral of secant squared times tangent is the integral of 1 plus tangent squared times tangent of x times secant squared of x dx, which is 1 plus u squared times u times du. And now this is a relatively easy integral using the techniques from Calc 1. And when I've computed that, I can convert back to functions of x. If n is odd, that is, the power of tangent is odd, I can use the substitution u equals secant of x, and remember the derivative of secant is secant times tangent. So I can use one of the tangents for this derivative, and now I also need at least one secant for this to work. So I need the power of secant to be at least 1 in order for this substitution to work. Then I can convert the remaining even powers of tangent to powers of secant using this formula, and I'm left with the integral of powers of u. Let's check it out for secant cubed times tangent x dx. I'm going to try to make the substitution u equals secant of x. So I split away a secant and a tangent for du. Let u equals secant of x. I have du is secant of x times tangent of x, and then secant squared is just u squared. So this is a very easy integral with this substitution, and then once I calculate, I can convert back to a function of x. You'll also find some extra examples at the end of your notes. Suppose m is odd, the power of secant is odd, so I can't use the substitution u equals tangent, and n is even, the power of tangent is even, so I can't split away a single tangent and secant for the substitution u equals secant. Then I can try to reduce the powers of secant using this formula. Or sorry, reduce 2 powers of secant using this particular formula. And then of course I need a method to deal with powers of secant. So for example, here we have the integral of secant times tangent squared x dx. I can't make the substitution u equals secant because you can check that out, see what happens. Because I have an even power of tangent here, it doesn't work. And I can't make the substitution u equals tangent because I don't have a secant squared for the derivative. So what I do here is I convert tangent squared to secant squared minus 1, and I convert this integral to the integral of secant cubed minus secant. And then of course our next topic has to be how do we integrate, or one of our topics has to be how do we integrate powers of secant or powers of tangent. Here's another possible combination of trig functions that you might have to integrate. Sine m times x times cosine n times x. So there are no powers involved here. It's just sine is applied to some multiple of x, and cosine is applied to some multiple of x. Well, we can use our trig identities in reverse. We have identities for sine A plus b, sine A minus b, cosine A minus b, and cosine A plus b. And you'll notice that on the right-hand side we have sums of things which look like the functions we're trying to integrate here. So we can reverse these identities to find identities for sine mx times cosine nx in terms of as linear functions of sines and cosines. And of course the things on the right-hand side here are much easier to integrate. Let's have a look at how we might apply this to the integral of sine 7x times cosine 3x. We use the formula sine mx times cosine nx is 1/2 sine m minus n plus sine m plus n of x. So this tells us that this integral is just 1/2 the integral of sine 4x plus sine 10x, and of course that's relatively easy using techniques from Calculus 1. How do we integrate powers of secant? Well, of course, secant to the 0 is 1, so this is a trivial function to integrate. And secant itself has an interesting integral. It's the natural log of the absolute value of secant plus tangent. And there's a trick to finding this out. The integral of secant is the integral of secant times secant plus tangent over secant plus tangent. And multiplying by the secant there in the numerator, we get the integral of secant squared plus secant times tangent over secant plus tangent. And now we make the substitution, u equals secant plus tangent, and we see we have its derivative here on top, and we end up with the integral 1 over u du, and of course that's the natural log of the absolute value of u plus a constant, and that's our result follows. What about secant squared? Well, of course that's the derivative of tangent, so its integral is tangent plus some constant. Secant cubed, we can use integration by parts on this. We let u equals secant, dv equals secant squared, and carry on from there. And in fact, we can use integration by parts for secant to the n, for any odd power of secant, to find this reduction formula. And in essence, we can convert the integral of secant to the n, we can convert that problem to the problem of integrating secant to the n minus 2. Then in turn we can convert the problem of integrating secant to the n minus 2 to the problem of integrating secant to the n minus 4, and keep going until we get to secant to the 1, which we can integrate as above. Powers of tangent. Well, tangent itself is easy to integrate. We just write it as sine over cosine, make the substitution u equals cosine, and we find that it's the natural log of the absolute value of secant. Tangent squared is secant squared minus 1, so its integral is tangent of x minus x. And tangent cubed is secant squared minus 1 times tangent. So I get secant squared times tangent minus the integral of tangent, and that's relatively easy. We use the integral of tangent from above, and we make the substitution u equals tan x here to get tan squared over 2 minus the natural log of secant here. And of course, remember, secant is 1 over cosine, so that's plus the natural log of cosine. For any n greater than or equal to 2, we can also derive a reduction formula for powers of tangent, and it looks like this. We can go from the integral of tangent to the integral of tangent to the n minus 2 to the integral of tangent to the n minus 4, etc., etc., etc.